Right. Hi, everyone. This is Michael, the TA. I was talking with other TAs today, and we all found that we were in a similar situation where this question number 5 of recitation 2, we either were very rushed when we talked about it in recitation, or we didn't get to it at all. I know I, in one of my recitations, did not get to it, so I thought it would be a good idea to make a little review video about the pH regulation in the blood. pH regulation in the blood is really robust, and we talk about two ways it's regulated in Biochem 4511. One way is through the lungs, and the other way is through the kidneys. Even though this question mainly talks about the kidneys, I think it would just be good to talk about the lungs as well, as it gives just like a bigger picture of the subject in general. So the main component of our blood buffer is bicarbonate, which, if you were not aware, is HCO3. This is bicarbonate. And bicarbonate really gets into your body. It can be a number of ways through metabolism and stuff like that. But the main way that we're going to talk about is through the carbon dioxide in your air. So you start off with carbon dioxide as gas. And this actually can come into your lungs. And, your lungs breathe in a lot of stuff. It breathes in oxygen. It also breathes in carbon dioxide. And this carbon dioxide comes in and it mixes with your blood in your lungs. So it mixes and some of it becomes aqueous. From here, the carbon dioxide undergoes a chemical reaction with water to form carbonic acid, which is H2CO3. This reaction of carbon dioxide to carbonic acid is a spontaneous reaction, but it really does not happen at that fast of a rate. I'm looking at a glass of water sitting on my table right now, and this reaction is definitely happening, but it is nowhere near the rate that would be needed to produce this carbonic acid that is necessary for the blood buffer system to exist. So the way our body compensates for this is that it actually has an enzyme called carbonic anhydrase that speeds up the reaction of carbon dioxide to carbonic acid. So now we have a lot of carbonic acid, and this can decompose into H plus and our bicarbonate. All right, so this is an equilibrium expression. This is something I would commit to memory. It's very important that you know for the exam coming up, definitely, but also just have a better understanding of how this buffer system works. So we're going to first talk about the pH regulation through the lungs. So our blood's pH, it exists around 7.4 is the average. And it really has a narrow range. It can have a high end of a pH of 7.5, or it can have a low pH of around 7.3. So this is what is really remarkable about this buffer system. In order to keep you alive, these systems in the lungs and the kidney really have to keep the pH within the range, within a 0.2 pH range. So that's just something to keep in mind. Now, even though the range is from 7.3 to 7.5, these extreme values of 7.3 and 7.5 are not an ideal pH that you want your blood to be at. So we're going to first talk about some mechanisms in the lungs. So imagine that your pH right now is equal to 7.3. When your pH is 7.3, it's lower than the ideal 7.4, which means that you have a higher H plus concentration than normal. When your H plus concentration is higher than normal on this equation, see I put the red arrow here, what's going to happen is your body will actually try to use Le Chatelier's principle to even out the equilibrium. So you want to decrease the amount of H plus. And the way it does it by Le Chatelier's principle is shifting the equation from the products here on the right side over to the reactants on the right side. So you use Le Chatelier's principle. So what's going to happen is you're going to start expelling more CO2. And one way that the body does this to expel CO2 is through hyperventilation. So sometimes hyperventilation is thought of as a way to actually bring in more air because you're breathing really fast. But what is really happening is that you're breathing off more air. So when you breathe off more air, you're going to be breathing off more CO2. You're going to have less CO2 inside your body. When you have less CO2, the equilibrium is going to shift to the left to make more CO2, and you're going to end up decreasing the concentration of H plus now, which will increase the pH. And so if you increase the pH, you are resolving this initial scenario of 7.3, and you are a little more happy. So you're going to be around 7.4 again. All right, now imagine that your pH is high, you're in alkalosis, and you're around 7.5. So as a reminder, when you have a higher pH than normal, that means that your hydrogen ion concentration will be higher than normal. If your pH is higher than normal, your hydrogen ion concentration will be lower than normal. So up here on this equation, we're drawing this green arrow. The hydrogen ion concentration is lower than normal. And so what's going to happen now is you're going to use Le Chatelier's principle again, but you're going to start shifting towards the right side. And so what your body is going to be trying to do is actually increase the amount of CO2 at this input. And it can be either at the gas phase, or maybe you can increase the CO2 at the aqueous phase. All that's mattering is that this will now shift the equilibrium towards the right side. Now, there's kind of two ways that the body can do this, which are not ideal. And they're to either slow breathing or stop breathing. And again, I don't think these are ideal things that we want to do because we want to be living, but just for the sake of the chemistry of this equilibrium, we would know that if we slowed our breathing or stopped breathing, there would be less CO2 that's released, and our body also produces CO2, so there will be a buildup of CO2, which will then shift this equilibrium here towards the left side and eventually increase the H plus concentration, which would decrease the pH, and we'd be possibly back around 7.4. Now again, I don't think it's good to hyperventilate, and I really don't think it's good to stop breathing, I don't want to stop breathing. So this is kind of where we have a more robust system in the kidneys that is more involved in our pH regulation of our blood using the bicarbonate buffer system. So this is really where our bicarbonate is going to be the star of the show. So now we're going to focus on our kidneys. This starts the way Dr. Wu wants you to know it, is that say you have a bunch of blood from your body and you have vessels coming in, and you reach this part where it comes to the structure called the Bowman's capsule. And what the Bowman's capsule does is it filters all of the bicarbonate in your blood. All of the bicarbonate in your blood passes through here, and it's filtered through the Bowman's capsule. So this is your blood, and you have HCO3 coming into it. Next to your Bowman's capsule is another part of your kidney called the proximal tubule cell. And what's going to happen is now the built up concentration of bicarbonate is going to react with something, and this proximal tubule cell is actually going to supply an H+. And so we're going to do a little reaction here, and these two are going to react together to form our carbonic acid. This carbonic acid can further be decomposed by our same carbonic anhydrase enzyme that we used up here. It's going to be decomposed into water and CO2. From here, our water, that's just a part of the cell. It's not super significant, but our CO2 is what we're looking at here. This can diffuse through the membrane of the Bowman's capsule in the proximal tubule cell, and it enters the proximal tubule cell and then reacts with some more water in there. Through the same enzyme, carbonic anhydrase, as we had back here, it reacts and it forms carbonic acid. And then this carbonic acid can decompose into H+ and our bicarbonate. Our bicarbonate now can be released into the bloodstream. So this is the bloodstream. So the whole point of the system is that you have this initial blood over here, and it essentially acts as a filter. The bicarbonate's filtered through the Bowman's capsule, and then it is eventually released into the same bloodstream later. And it's just another way that we're able to filter stuff in our body. But the way this bicarbonate is released is a selective mechanism. And this again relates back to our equation we had up here. So I'm going to rewrite it again, where our CO2, or gas, is going to the CO2 aqueous, can be made into carbonic acid with carbonic anhydrase, which will decompose into H+ plus HCO3 minus. All right, so now we are going to deal with these same scenarios of different pHs and just see how this structure of the Bowman's capsule can help regulate the pH. So let's start off if we have a pH of 7.3. So this is what the question was asking about. If we are in acidosis, how we're going to maintain a normal pH. Again, when we have a pH of 7.3, our hydrogen ion concentration is higher than normal. So we're higher right here. I'm going to try to make sure everything's in view. If our hydrogen ion concentration is higher than normal, we're going to want to get that lower. And so what we're going to do, we're now using bicarbonate as our kind of tool to change the pH. And so by Le Chatelier's principle, what we're actually going to do is we're going to actually release a lot of this HCO3 into the bloodstream. So if we increase and add a lot of the HCO3 to the bloodstream, this will then shift the equilibrium towards the right and eventually decrease the amount of H+. So that makes sense. If we add more HCO3, add more bicarbonate to the bloodstream, the equilibrium is going to shift to the right, and we're actually going to lose H+. So if we lose H+, we're going to increase the pH, and hopefully we'll be back to around a pH of 7.4. All right, now if we're in the other scenario where we have a pH of around 7.5, this means that we have a hydrogen ion concentration that is lower than normal. So again, I'm just going to write on this equation. If we have a lower hydrogen ion concentration than normal, what is actually going to happen in the kidney is that there will be less HCO3 now released into the system. So if we have a lot less of this HCO3, this bicarbonate that's released, the equation is going to want to come and it's going to want to shift itself to the right now. So we have less of the products, we have less of these products, and we're going to want to make more, so we're going to shift towards the right. And so when we shift to the right, we're going to end up increasing the pH. We're going to end up increasing the hydrogen ion concentration, and by increasing the hydrogen ion concentration, we're going to end up decreasing the pH. Going back to this picture, this representation of the chemical reactions going on in the kidney, it's pretty complicated, and I know I've gotten questions as to why it's happening. It might seem a little redundant. I would say, first of all, think about what's going on with the diffusion of the CO2. What we're doing is we're taking a charged bicarbonate molecule and making it into a small nonpolar CO2 molecule, which can pass the membrane of the Bowman's capsule into the proximal tubule cell. So that's one thing that's going on. For more of this, I'm not a physiology TA, and I do not know the entire story. I think it's, nephrology, the study of kidneys, is one of the most, difficult subjects you can study in medicine. So I don't think obviously I don't claim to be an expert. I would say Dr. Wu even thinks it's probably a little difficult. Just know that this mechanism happens, and there's some sort of way that this is necessary for the body. And then the last thing I just draw your attention to is that remember that this kind of reaction is a cycle. This last H+ that is decomposed from this carbonic acid here is actually used in reaction with the bicarbonate to form this original carbonic acid. So I think that's just a little cool. But yeah, that is essentially what would have been covered in recitation if we had more time. Again, sorry, this is a very jam-packed week. I know next week, Dr. Wu said the recitation is going to be a little more chill. Beyond that, I know that this scenario, even though I explained this, it can definitely still be confusing, so feel free to reach out to me with any questions or any of your TAs. I'm sure we'd be happy to help you. All right, I hope this helped, guys, and have a good night. Bye-bye.